Good morning. So today I'll continue with photoelectrochemical water splitting, which I started in my last lecture. What we discussed in the previous lecture was that what is the importance of green fuel for the green energy and green technology. Of course, we should say that with green economy. And hydrogen plays a very important role in entire green economy system, because the fuel is the one important thing which actually creates contaminations in the environment. So therefore, one is to look for green fuel or a fuel which does not emit carbon during its production or process. So hydrogen can be one among them, and this is what the present research is going on, and this is what we discussed in the previous lecture. Hydrogen being a light element, it can be generated and it can be stored also and can be transported also. Okay. So if we think about the next generation of automobiles or green automobiles, one of the important choice of fuel is hydrogen. Okay. Now, to various processes of hydrogen production, we discussed one process, that is photoelectrochemical water splitting, which is actually used to produce green hydrogen. And as the name suggests, that it is actually the hydrogen is produced by photon. Okay. Therefore, the energy of sunlight is converted to the chemical energy by in PEC water splitting process, and hydrogen is generated, and it is completely zero carbon process. Okay. So we discussed about the reaction of production of hydrogen by PEC along with some other process by which one can produce hydrogen. And then we also addressed in the previous lecture what is the importance, how one can choose material for PEC water splitting. So what are the onsets of 1.23 electron volt are the onset, is the onset energy, you can say, for the splitting of water. Okay. So what are the conditions for a material for a good water splitter? So if I write the conditions, the first one is the band gap of the material should be 1 point higher than 1.23 electron volt. Okay. So this is the first condition, and the second condition, band edges should be adjusted with above condition. Okay. And the third is the material should be stable in chemical environment that we are using. Okay. So these are three important properties of the material for a good PEC water splitting process. Okay. So if I just want to highlight these particular first 2 points, 1 and 2, then I can make a drawing as I made in the last class, that we have this potential which is as per standard hydrogen electrode, Okay, and this is one line. I can say that this is 0 electron volt line, potential energy line, all right, and this is 1.23 electron volt line, which is required for oxidation. Okay, so if when photon falls, let us consider this. When I talk about this 1.23 electron volt, what I mean is that the electron, this is the valence band, this is the conduction band, and electron jumps from valence band to conduction band, creating one electron hole pair. Okay, and then this electron hole, actually if they have enough mobility, they goes to the respective electrode in the process, and then this is again we can write in this way that it generates hydrogen through hydrogen evolution reaction, okay, and it generates oxygen through oxygen evolution reaction. So, this is a picture which we get when we really want to make a material or want to work with a material for PEC water splitting, and look at exactly where the conduction band minima or valence band maxima should lie. Okay. So, there are many materials which are of this choice. I can just see it in this plot. If you look at that, there are several materials which actually their conduction band minima and valence band maxima, actually you can say that they are straddled between these two, HER and OER reaction. Okay, this should be O2. This is O2. Okay, so you can see that one material, they are all semiconducting material because the band gap is typically of the semiconductors. So, you can see that this first material, which is having band gap 1.8 electron volt, gallium indium phosphide, here actually the conduction band minima lies and here the valence band maxima lies. So, you can see the valence band maxima is just slightly above the conduction, uh, this potential line 1.23 electron volt potential line, so or OER line. Okay. So, similarly if we consider gallium arsenide, this also we have the same condition. Now, if we consider cadmium sulphide, then you can see this cadmium sulphide. So, you can see that conduction band minima is slightly above the HER line and valence band maxima is slightly below the OER line. Okay, so this is a good condition. CDS with an energy of band gap energy of 2.25 electron volt, and the position of the band edges looks very good. Similarly, CDSE, silicon is a non good material for that, because you can see the valence band minima is much below, is much above this OER line. Iron oxide is sometimes considered as a material, although valence band maxima is lower, but conduction band minima is somewhere here, and WO3 is also used. TiO2 is actually the material which was used for the first time for PEC water splitting reaction, okay, in 1972, and then still people are working, lot of work is going on with titanium dioxide. But if you look at titanium dioxide, then you can see that its band gap is much higher as compared to 1.23 electron volt, which is, you can see, the onset potential for PEC, and the band edges are also locating in the manner that we want. However, the only problem with TiO2 is that its band gap is quite large. With 3.2 electron volt is quite large, and therefore lot of the photon gets transmitted through TiO2. What we require is strong absorption of photon in the band gap. inside the material. But then we will see later how one can improve the absorption of light in TiO2 for PEC water splitting. But why we are interested in TiO2? The reason is that it is actually chemically stable. This actually satisfies the third condition. Okay, so TiO2 seems that it satisfies all these three conditions, and therefore we will focus sometimes the research on TiO2 as a PEC water splitter. CO2O is also a PEC water splitter. Zinc oxide is also used, and some of the materials have been used for PEC water splitter in their nano phase or nanostructured form. So those we will discuss later, but we get a rough idea about what are the materials that we can choose as a PEC water splitting material, and begin with, if we have some rough estimate of their band gap and the position of the band edges with respect to HER and OER line, it will help us in selecting the material for further research. So the question is how when we take a semiconductor and metal combination, one can have PEC water splitting with two metal as two electrode as a combination. Okay, one can have one semiconductor, one metal, p-type semiconductor, one metal as a combination. One can also have one n-type semiconductor and another metal as a combination of electrodes, or one can have two semiconductors as combination as n-type and p-type. Okay, so let us look at when we have a combination of n-type semiconductor with a metal. Okay, so the how it happens. So if you look at this, so in the left hand side we have a semiconductor. Okay, this is the Fermi level of the semiconductor. All right, and this is the valence band, and this is the conduction band of the semiconductor. So light actually interacts with this semiconductor. So entire setup is immersed in an electrolyte. So electrolyte is in between. All right. So what happens that when light interacts with the semiconductor, as I mentioned, that electron goes from valence band to conduction band. All right. So it creates a hole here and it creates an electron here. So what happened to this electron? This electron actually finds a path here. It goes in this direction and comes to this metal electrode or counter electrode. Okay. So this is the Fermi energy level of the metal. Okay. So now I have one hole and electron combination which is being generated by interaction of photon with the semiconductor, and then the hole actually goes in this direction and it interacts with water. Okay. So it is actually the water is split into H plus and OH minus in an electrolyte that we know from chemistry. So hole actually interacts with OH minus and it gives two water and one oxygen. Okay. So this is in this electrode what we see, that oxygen evolution reaction in the semiconductor electrode. Okay. The other side, the electron goes in this direction. Okay, and then it comes to this particular the electrode, metal electrode or counter electrode, and this is water molecule. So it interacts with the water molecule and it again gives 4 OH minus into H2. All right. So this is a hydrogen evolution reaction. So we can say that at semiconductor side, n-type semiconductor side, we have oxygen evolution reaction, and in the metal electrode side we have hydrogen evolution reaction. Okay, so if I just try to again understand that what is the process and how this is actually creating hydrogen and oxygen by splitting water in stepwise, then we can say that again the excitation of n-type semiconductor, which is one electrode, okay. So generation of electron and hole, this I can make an arrow, generation of third is the suppression of recombination, and then we have OER and HER. This is at semiconductor electrode, and this is in metal electrode. So this actually gives a complete picture when we work with the semiconductor metal combination for the generation of hydrogen or oxygen or splitting of water. Okay, so that means when we think about any PEC water splitting system, which we will discuss in the next lecture, it is clear in our mind that there will be two electrodes. One would be one semiconductor, another is metal, or these both could be semiconductors. Okay, and then the light interacts with the electrode, and eventually all these processes are followed and the hydrogen and oxygen evolution takes place. So there are three essential requirements. We should have a good the photoelectrode where the excitation is possible, okay, and the light absorption is also maximum or optimum light absorption, and then we have a good electrolyte where the transport of charge carrier takes place efficiently, and then we have a counter electrode which can create the path for electron and trigger the HER reaction. So in future when we will discuss about the PEC water splitting system, we have to keep all these points in our mind. Okay, so this gives an overview of what is the PEC water splitting process. Okay, along with that it gives us an idea about what type of material we can choose for PEC water splitting process. So now we will see one important thing, that how this reaction and energy in a cell is considered. So if I just consider a cell, again I take say an n-type semiconductor, and then I have this is the energy scale, okay, and then you can say this is a 0 electron volt line and this is 1.23 electron volt line, and there is another electrode there. So what we have discussed, suppose it is n-type semiconductor and this is metal. So when we consider the energy and reaction, that when light falls here, the electron goes say from valence band to conduction band and creates an H plus and E minus here, and as I discussed that H plus interacts with OH minus, okay, and it triggers an OER reaction here, and electron which finds a path here, okay, suppose this is a bias, it comes to this particular electrode and it interacts with H2O or interacts with the H plus ion and is triggered say HER reaction. Okay, so this is what is typically happening. So when, and we have in between, we have electrolyzer. Okay, so this is what is happening in a PEC water splitting setup for generation of hydrogen. All right, and as I mentioned that this hydrogen is completely carbon free. Okay, this entire process is completely zero carbon emission process, and we get hydrogen in this process. Okay, so this gives us an overall idea about PEC water splitting, and we have to understand little bit about the fundamental question that what energy, so far whatever energy I have discussed, it is only on the scale of the hydrogen evolution reaction and oxygen evolution reaction. That means in type of these two lines in between, how these band edges straddle. So this is one important point in energy of the PEC water splitting process. Another important point is when we bring this semiconductor very close to the electrolyte, then what happens? Okay, so I know we have a definite energy levels for a semiconductor or energy bands from a semiconductor. So for a semiconductor, we have a valence band and a conduction band. Okay, now what about the electrolyte, which is very close to the semiconductor? So I can just imagine that electrolyte, now I am not talking about semiconductor, I am just talking about electrolyte. So and this is the, say, the energy line as per standard hydrogen electrode, and this electrolyte also I can make two bands. How? I can have a sort of empty band, this is an empty band, okay, and I can also have a filled band, this is a filled band. I am just correlating with this with valence band and conduction band of semiconductor. Almost try to give a similar picture. So this I can say the density of state DOS, which we discussed many times before, corresponding to for reduction. Okay, so I can consider that these are certain energy state which are responsible for the reduction reaction. So I can say that this is density of states which are filled for the reduction reaction. Okay, and then I have an empty band and I call it density of state for oxidation. Okay, so now I can have a sort of Fermi level exactly similar to what we do in case of semiconductor. All right, a Fermi level can be drawn and I call it EF redox. Okay. All right, so this is a picture of, we already discussed a lot of about the electrolyte and electrode combination, but I did not bring this picture before. So now I bring an energy picture for the electrolyte also, where I define a density of state corresponding to reduction and density of state corresponding to oxidation. Okay, and the reduction band is the density of states they are filled, and the oxidation states they are empty, and in between we have a Fermi level, or which is EF redox. So that means I have almost similar kind of the feature or the property which I try to make here, almost similar to the semiconductor. So now the question is, when such system is working together, that means when a semiconductor as well as an electrolyte are brought together, okay, so then what happened energetically? So let us look at, so this is semiconductor, I have conduction band, valence band, I have a Fermi level, okay, and this is an electrolyte. This is semiconductor, and this is electrolyte. Okay, so it is also having a oxidation and HER, density of state, and then it is having a Fermi level EF redox. So they are now separated. All right. So the semiconductor and electrolyte, they are not touching each other. So now I bring them together. That means when I immerse a semiconductor electrode on the electrolyte, then what happens? What happens to this energy? Actually, now they are closer. So there will be a little bit of band bending when electrolyte touches the semiconductor, and then there will be same equipotential line. So both Fermi level will be in equipotential line. Okay. So now I have electrolyte, and there is a common Fermi level. Okay, this is energy scale. All right. So the first step is that they are separated and they have different energy levels. And now the second step is that they are brought together, this semiconductor and electrolyte. So there will be a band bending of the semiconductor, and the Fermi level will be in equipotential line. So the third situation is when I shine light on the semiconductor. So when light falls on the semiconductor, immediately lot of electron hole generation will start, okay, and then electron will go from valence band to conduction band. So what will happen when electron goes from valence band to conduction band? Fermi level in this side will go up, okay, and Fermi level here is remaining same. Okay, and then you have a potential generated here. Fermi level will go up because conduction band will be more populated. Fermi level will go up in the semiconductor, and then there will be potential generated here. This is called photopotential or photovoltage. Okay, this is important because whenever we will discuss in future, we will discuss in terms of photovoltage, in terms of the efficiency or the current density generated in a particular PEC water splitting system. So this gives a very clear idea how photovoltage is generated. So when we talk about the photovoltage of any PEC water splitting setup, we will understand that in terms of how much is the difference of energy of Fermi level energy and redox potential energy. Okay, this is now EF redox potential energy. What is the difference? So if we want to have more photovoltage to be generated, we have to have more difference of these two energy levels. Okay. So these sort of these things earlier also we discussed in case of dye sensitive solar cell and quantum dot sensitive solar cell. Okay. So now today let me just summarize the thing. with something called benchmark, because when we want to go from our basic understanding to the the technology, we need to set up certain benchmark. Okay, so there are several benchmark, but there are some standard benchmark which have been designed for PEC water splitting and for a normal system. Of course, you will see later there are a lot of architecture in the PEC water splitting setup, and therefore this benchmark may vary depending upon which PEC water splitting setup we consider. What I mean is that suppose I just consider a simple PEC water splitting setup where we have a cathode, we have an anode, two electrode system, we shine light in that, and then we generate hydrogen. Okay, but there are some PEC water splitting setup where a photovoltaic cell is also connected with this PEC setup. So in that case, the efficiency of the cell or the kind of the benchmarks, it changes. Okay, so for a simple PEC water splitting setup, if we look at the benchmark, then we can have two particular aspect. One is the requirement of the material, another is the photoanode characteristic. Okay, so for a simple setup, we should have a conversion efficiency of about 10%. What is the conversion efficiency? Conversion efficiency is in terms of solar to hydrogen conversion efficiency. How much solar energy you are using and how much hydrogen you are generating. That is called the conversion efficiency. Okay, so 10% is a good number. However, people have shown much higher these days with a complicated PEC reactor that we will discuss little later, and the current density typically of 10 to 15 milliampere per centimeter square in a PEC setup. Okay, in some cases people have also shown almost 20 milliampere per centimeter square, but they are very specific case which we will discuss later. Material durability is typically greater than 2000 hour. Okay, material should be stable for more than 2000 hour, and it should be economically feasible. There is one question always comes with hydrogen energy, that it is not economically feasible. However, if we choose the material in such a way that they are abundant material, then we can make entire PEC system as economically feasible. Okay, and we have already, now the second benchmark comes from the photoanode characteristic, whose band gap energy is typically, as I told you, this should be more than 1.23 electron volt. The benchmark is typically 2 electron volt. Okay, and then in order to produce electron hole charges, there should be strong optical absorption. That is important, that the photons which are falling on the material should get absorbed. Okay, and then the lifetime of the charge carrier should be long. All right, because if the charge carriers recombine, as I mentioned before, then they will not be transported, and therefore the HER and OER reaction will not take place efficiently. So their lifetime should be high. And then I also discussed that it must straddle with the redox potential of water, that I clearly explained on the basis of this HER and OER line, and I showed that how the band edges should be straddled with respect to the potential of water and stability in strong electrolytes. This particular point we have addressed, and that is the reason why TiO2 was used, and TiO2 still people are using, and we will also see that how nanostructured TiO2 these days people are using for PEC water splitting, and it should have good catalytic property and it should be cost effective. Okay, so all these the properties or the qualities in terms of material, in terms of the photoanode, there should be certain benchmark. So in the next lecture we will discuss several PEC water splitting setup with different materials, okay, or the combination of materials, and then we will look at that how much the benchmark people have already shown, or what is the typical values in terms of this benchmark people have already demonstrated.